So welcome, hello everyone, and welcome to my channel. And today in this video I would be explaining about uh, how to find adiabatic flame temperature, or how to estimate the adiabatic flame temperature for constant pressure combustion. So for that uh, we consider a control volume like this. From one side a fuel and air is injected, and in this chamber, that is a constant pressure chamber, and inside this chamber combustion happens, and then on the other side products is released. The products of combustion are released. And so why and how the temperature of the products will be called as adiabatic flame temperature. I mean, the temperature of the products will be considered as adiabatic flame temperature when there is no heat transfer happening out of this control volume. It means that the heat transfer is zero. So in this case, the whole heating value of the fuel is being converted into the flame, and then the temperature of that flame will be called as adiabatic flame temperature. So this is how we call it as an adiabatic flame temperature. Adiabatic means itself that there is no heat transfer taking place in this combustion chamber. It means that there is no heat transfer taking place. Okay, so that's why it is called adiabatic flame temperature. It means the whole heating value of the fuel is being converted into the flame. I mean, the temperature of the products will be called as adiabatic flame temperature. So now, when there is no heat transfer, then the temperature reached inside the combustion chamber is adiabatic flame temperature for constant pressure combustion. Okay, so now our funda is how to find this adiabatic flame temperature, or we can say how to estimate this adiabatic flame temperature. So for that we need first law of thermodynamics for this flow process, I mean steady flow. So we assume that we have some assumption in this, like we assume the steady combustion process. I mean, we assume that the combustion leads to a steady state condition. So in that condition we estimate the adiabatic flame temperature. Okay, so now as we know from steady flow energy equation for using first law for constant pressure or control volume, the first law can be written as like this: Q minus W, that is heat transfer, this is work, and this is enthalpy terms, and this is velocity terms, and this is potential terms. So in our configuration there is no velocity consideration though, so it will be 0, and there is no potential difference, I mean the gradient in the height, so this will be 0. So only the term remaining will be the enthalpy term. Okay, and then as we assume that as we know, for finding the adiabatic flame temperature, we consider that we assume that there is no heat transfer, so this term will be 0, and there is no work transfer. I mean, there is no work input or output is being not taking place in this analysis. So it means that the product from this equation, the total enthalpy of the product is equal to total enthalpy of reactant. So it means that HP is equals to HR. It means that the total enthalpy of product is equals to total enthalpy of reactant. So this can be written as this, like summation of every every species of product and every species of reactants. Okay, so now here we will consider an example to understand how to estimate using first law of, like for a methane. The reaction, the initial condition of the methane is like it is like at 298 Kelvin and 1 atmospheric pressure. That is ambient standard conditions, and combustion is taking place, and products will be this. So for this we assume that for this case we are assuming that there is stoichiometric combustion is happening. So it means the fuel is totally converting in CO2 and H2O, and so the temperature of this product, that is called adiabatic flame temperature. Okay, and we need to find that. So the temperature of product is adiabatic flame temperature in this case particularly. So we need to find that. So we can write the total enthalpy of reactant as the summation of all the reactants, like the mole of methane into the enthalpy of methane. Similarly, mole of oxygen into enthalpy of oxygen, mole of nitrogen into mole of enthalpy of nitrogen. Okay, so we can write this in total enthalpy of methane as enthalpy of formation of methane plus change in enthalpy of methane if there is any increase in temperature from ambient, that is this. Okay, so as of now there is we assume that the temperature of the reactants is at atmospheric condition or standard condition, so this will be 0. Similarly, this will be 0. So similarly, this will be 0. So what terms will be remaining as enthalpy of formation of methane and twice into enthalpy of oxygen, 7.52 enthalpy of formation of nitrogen. Okay, so this is the enthalpy of reactants. So also in this case we know standard enthalpy of formation of naturally occurring gases like oxygen and nitrogen are 0. So these terms will be 0. So the only thing remaining will be enthalpy of formation of methane. So similarly, like for products, as we know, in the products there is CO2, H2O and N2. Sorry. So similarly we can write mole of CO2 into enthalpy of formation of CO2 plus change in enthalpy of CO2 if there is any temperature change from ambient. And as we know, the product is at adiabatic flame temperature, because we are estimating that because there is a combustion taking place, and the enthalpy of products will be very much higher than the atmospheric conditions. Okay, so and that temperature we need to find. So and that is that this delta H is like this: how much enthalpy rise is there with respect to ambient. Okay, so this delta H is, so how to get this value? So we get this value from any thermodynamic data table. You can find it in any thermodynamics standard thermodynamic books on the back side of any book, a standard book. Okay, so from table at some temperature. Okay, so now we want to calculate the total enthalpy of reactant. So as we discussed that total enthalpy of a reactant was like only remaining like this term, the enthalpy of formation of methane. Okay, so the enthalpy of formation of methane is this value. This value I got from a table, directly from table we can get. Okay, similarly for enthalpy of products we can write it as this, as we written earlier, as this above. So similarly for enthalpy of product we can write as this. So in this case we can see there is enthalpy of formation of CO2, because we have basically three terms in the product side: H2O, CO2 and N2. So we know enthalpy of formation of N2, this is at a standard condition. Okay, this is always standard condition. It means that this is always at this is always at standard conditions. So in this case for naturally occurring nitrogen, it should be 0. Okay, so what terms are remaining, like as enthalpy of formation of CO2 plus enthalpy of formation of H2O 2 into enthalpy of formation, because this is 0, so it will vanish. Okay, what are the other terms? The terms will be this term, and this enthalpy difference is because due to the combustion taking place, and this term is not known exactly, because this term this enthalpy change will be vary according to the temperature achieved in the adiabatic condition, that is adiabatic flame temperature. So this temperature we need to find. So our basic funda is to find this temperature. So we will assume this value is at particular T. We will see later how we can find the adiabatic flame temperature, this T temperature. So this term written as this term is written like this, and this term is written like this. Okay, so this is the whole enthalpy of product, and this is the whole enthalpy of reactants. Okay, now so now putting the value of enthalpy of formation to these values, as you can see, for CO2 we can directly obtain from table, for H2O we can directly obtain from table. So I have already put that data from the table, thermodynamic table, as this. So now we will equate the enthalpy of product equal to enthalpy of reactant. This as I already explained this, we got this from first law of thermodynamics. Okay, so now this is enthalpy of product. We got this now. This whole term is, we got this like this. We can write this and the equal to sign, and this enthalpy of reactant we got earlier like this. So we will write like this, we will equate like this. So this we got from this this adding and subtracting, we got we will get a simple expression like this. So this is enthalpy change of CO2 with respect to temperature, some temperature. Okay, similarly like for H2, for N2, and this equates like this. So what we need to find is we will see at which temperature the LHS becomes RHS. This means this one. So that when the LHS becomes equals to RHS at some particular temperature, and that temperature will be called as adiabatic flame temperature, and we need to find that by simply iterating, like, okay, how, like we will put some value, we will see some value for enthalpy change for CO2 at some particular temperature. Suppose like we will put some like we'll get some temperature like for 1500K. Okay, for 1500K, let's say for 1500K first iteration, for T 1500K, we will see the LHS value, and we will sum up these and see how what is the value of LHS. If it is lesser than this, then we will increase this value, and we will increase this value further until and unless we will get LHS equals to RHS. And that temperature, like by just simply varying this, and 1600, 1700, okay, 1900, 1800, 200, 2000, sorry, 2000, 2100. So that final temperature at which the LHS will be equal to RHS, and that temperature will be equal to the adiabatic flame temperature. In this way we can find we can estimate the adiabatic flame temperature of a full particular fuel. Thank you, and if you like this video, kindly share and like and subscribe my channel. Thank you.